Hi, welcome to another lecture on linear algebra. Today we are going to talk about the idea of proofs. We introduced you to several formulas in the previous lecture. Today we are going to talk about where do the formulas themselves come from. Let's go ahead and start this topic. So proofs of basic theorems and formulas. Perhaps the most famous theorem in mathematics is the so-called Pythagorean theorem or Pythagoras' theorem. In the right triangle with the sides AB and hypotenuse C, we have a squared plus b squared equal to c squared. Now, our main question is, why is that so? Well, in our approach to mathematics, we can take one of 2 points of view. One is a kind of essentially end-user mathematics. End-user mathematics says, well, I have a particular right triangle, perhaps the sides are say 3 and 2, and tell me what is the hypotenuse. So we plug in 3 and 2 here and we get 13 for the other side. 3 squared plus 2 squared is 13. Take a square root and then we are done. Next level of mathematics is, well, why is this statement itself true? It's a higher level mathematics. And establishing the truth of such statements is done by the idea of a proof. So some of the linear algebra classes concentrate mainly on proving everything that is stated, and some others starting viewpoint on the course perhaps goes from this point of view, which is what we have adopted. But I wanted to just give you a flavor of what happens when you try to prove some of the statements, and the ideas that we had presented in the previous lecture are easy enough for us to take a short detour and bring up the idea of proof. If you take a next level linear algebra class, essentially the entire semester goes according to lectures similar to this, not based on geometry but on linear algebra. However, the idea is to establish everything with a proof. Okay, to prove something you have to start with certain assumptions or axioms, have rules of logic that tells you how to proceed, and then step by step you go through a chain of ideas and you arrive at the final conclusion. For us to get to our destination quickly, let's go after some ideas we can agree on. One is, if you have a rectangle with the sides A and B, well, what would you say the area of that is going to be? Well, area of a rectangle is just going to be A times B. We agree on that one, that the area is that. Next up, well, what if I have a right triangle and the sides are A and B? What's the area of that? Well, you might say, well, let's complete our rectangle, and this is half of that rectangle, so it stands to reason to say that the area of this is half of the area of the rectangle we had over there, which is A times B over 2. In a special case, if the sides were equal, well, you will have a square. If this is A and this is A, in that case, as far as the algebra is concerned, we simplify this thing and write it as A squared. Okay, that is some preliminary ideas. Now, how do we come across this particular formula? Before we dive into the details of that, let's just take a historical detour here. This is perhaps the most famous theorem in mathematics, so it has been there since antiquity. There are several hundred approaches to it. You see the traces of this thing in a variety of cultures. Greeks, Mesopotamians, Indians, Chinese, and so on. Each of them had a particular approach to this, and among them the Greeks developed the idea of geometry in a systematic way. So you see their names on many of these essential ideas. So this is referred to as Pythagorean Theorem from 2300 years ago, but the same thing does show up in a variety of other cultures. Now, just to show you, let's go take a look at so there is this website claiming there are 367 different ways of approaching this and proving the idea. Here is a page on Wikipedia where you can see animations quickly showing you why this theorem is true. If you want to dig deeper, there is this other website, cutthenut.org, where you can look at the proofs in a more mathematical and detailed style. So let's go ahead and take clues from one of these and develop our idea from that one. So what we do, taking approach of so-called rearrangement idea. The rearrangement idea is to cut and paste a bunch of triangles so that at the end you have either rectangles or squares whose areas you know, and then arrive at the final formula. So here is one approach to this. We draw length A and then length B, and then we try to complete a square. So I will have let's say 1 2 3 4 5. I have here 1 2 3 4 5, and then so I'm going to make a square of side A plus B, and then inside of the square we see 4 copies of that original triangle we were talking about over here. So this is AB, and then again AB, and this is A and B, and this is A and B, and the interior side is going to be C. So this big shape is going to be, of course, a square, and the area of square is a square of the length of it, so that's going to be A plus B squared. Now the interior one is also square. You can reason one of two ways. Again, the idea of proof comes in here. One is that this angle plus this angle, the sum of these two angles, is going to be 90 degrees, and therefore what is left in the interior has to be 90 degrees as well. So the sides are the same, angles are 90 degrees, therefore it's a square. Now I go ahead and calculate the area of this big square. That's going to be A plus B squared. Is that right? From basic algebra, you know what's A plus B squared. It's A squared plus B squared plus 2AB. I go ahead and calculate the same area in a different way, which is to calculate the area of this interior square. So we agreed to show that by C squared plus, well, I have 4 copies of this triangle. Let me see if I can color it right. So I have 4 triangles, each of them of area of AB over 2. So that becomes C squared plus 2AB. Well, this area and that area is the same thing. Same area is being calculated. Here is A squared plus B squared plus 2AB. Here is C squared plus 2AB. These two have to be the same. That is A squared plus B squared plus 2AB has to be C squared plus 2AB, and therefore A squared plus B squared has to be equal to C squared. So this style of approach to mathematics is very different from what you typically go through in an algebra class or calculus class and so on. The pieces are being constructed out of essentially thin air put together, and then some final idea comes through, and that is the final proof of the theorem. Like in this case, we had the Pythagorean theorem. So admittedly, this is very different from mathematics that most students are exposed to, but it's a very good exercise to engage in and try to develop your mind in that direction. And if you are interested, then we'd like to talk to you about perhaps majoring in mathematics. Let's go ahead and take a look at the next formula we need over and over again in this class. Okay, Pythagorean theorem says what happens in a right triangle. Question comes up, well, what if your triangle is not a right triangle? What then? So we have something else. Typically you see this in your trig classes. They call it law of cosines. But here let me just go ahead and bring up the idea. Suppose I have a triangle, not necessarily a right triangle, and this side is B, this side is say A, this side is C, and this angle, unlike what we had over there, some arbitrary angle theta. What can we say now? Well, you have learned this thing, but let me see if you can. Okay, we said the idea is to try to pause and see if you can remember. You have taken a trig class for sure. So what is C in this case? In a triangle with the sides A and B angle between them theta, what is the third side? Okay, did you come up with a formula? Did you remember? So C squared is A squared plus B squared minus 2AB cosine of theta. So in case theta is 90 degrees, then cosine of 90 degrees is 0, and this expression becomes 0, and you have C squared is equal to A squared plus B squared. So when your triangle becomes a right triangle, this formula just becomes the Pythagorean formula we had. But this is a more general form of it. It has a corrective term here in case the angle wasn't 90 degrees. How do we go about establishing this one? What is the proof of this idea? So let's separate it from the previous one. What do you think? Well, sometimes in mathematics classes they do expect the students to come up with the idea of proof based on things that they have seen. Mathematics always is a chain of ideas, and everything is being built on top of something else we have already established. So if you wish, you can pause this video and see if you can crank up a approach to this. So in that case, if you're interested, again you pause and then you come back. But now let me continue. So the idea, of course, is to take this thing and reduce it to the previous case. So one way to do that here is to draw a perpendicular, and now you have two right triangles, and in that you can develop the ideas from the previous. So let me go ahead, call this leg X and this one H. Of course, this is X and the whole side is A, then what is left here is just A minus X. So first of all, on the triangle on the left side, let me just extract it and put it separately. So this was X, this is H, this is B, and this is theta. You remember what was the definition of cosine, ratio of adjacent to the hypotenuse, so the X over B, or in other words, X itself is equal to B times cosine of theta. So we need that as a side statement there. Now in this right triangle, what can we write? So I use the word right 3 times, but anyway, let's go ahead. We have C squared is equal to H squared plus A minus X squared. Is that right? And this hypotenuse, this leg, and this other leg. Let's expand this thing. So this is H squared plus a squared plus x squared. What else do I need to write here? Of course, minus 2ax. Now, what is h squared plus x squared? H squared plus x squared. Well, that is again another application of the previous theorem. That's gonna be just b squared, and then I have a squared minus, now let me write 2ax minus 2a. Instead of x, I write its equivalent expression, which is b cosine of theta. Well, we are done. Do you see? We established that c squared is equal to b squared plus a squared minus 2ab cosine theta. That, as we said, you see this thing as the law of cosines from trigonometry. Now you might be asking or objecting, why are you repeating trigonometry? Well, very importantly, that's actually what is behind the formula we had last time. We said dot product of two vectors, which was defined as multiply. Let's remember what this was the definition. Suppose a is a1, a2, say a3, as many elements as you might have, and b could be b1, b2, b3, as many elements as that one has, and then the dot product was multiply the first entries, multiply the second entries, multiply the third entries, and add them up, get one number at the end. That is what the dot product was. That was the definition of the dot product. Now, then we said there is another way of calculating dot product, that the dot product of two vectors was also equal to the length of A times the length of B times cosine of the angle between the two of them. So if I have a vector A and then I have a vector B, and the two of them make some angle theta, the dot product of these two, instead of using that formula, I can use length of this times length of that times the cosine of the angle between the two of them. Well, this statement is a claim. It needs a proof. We have a definition, and the next version of it requires a proof. Why is it that this is same as the previous one? Again, from an end user mathematics, end user approach to mathematics, what you say is that, well, length of this times the length of that times the cosine of the angle is equal to whatever dot product is equal to this, a1 b1 plus a2 b2 plus a3 b3. And if I've given you some of these numbers, you can calculate the other ones by this equation. Okay, that's fine. As a user, you can do that. But again, the question comes out at a higher level mathematics. So why is this statement itself true? Where does that come from? So that's what we are going to do here. And of course, you see the connection to the previous statement. We are making a chain of reasoning. And this statement in linear algebra is essentially same as what you saw in your trig class in high school, which was called law of cosines. They are really same thing. This is like more modern version of that one. So how do we go about establishing this? The idea is again very simple. We draw a triangle. So I'm going to redraw this picture again. So I have A and I have the vector B. Let's go ahead, use the little a as the length of this. So A is the length of the vector A. You remember what I said in the textbook, you see the length showed by double vertical bar. You see it already giving me a bit of a trouble. So it takes a long time to write that, and then when you have many of them, the situation gets out of hand using so many pieces. So I just used one, and more advanced books do the same thing. So this is same as that. In other version, you remember that the length squared had another expression which was a dotted with a itself. So the little a is going to be the length of this one, the little b is going to be the length of this one. A and b are the names of vectors, and now what I need is to complete my triangle. So let's call this thing vector c, which is now going to be a minus b. Remember how to subtract? And you always have a little bit of a problem. Capital C and little c look like each other, but try to be careful about using that. Okay, so we need that to know that this third side is the difference of the two vectors. The vector for the third side is the difference of the two vectors for the other two sides. Now let's go ahead and call that angle theta, just so that it matches everything we had over there before. So in the law of cosines, we calculated little c squared. So here we are going to start with the same thing. We are going to say take the vector c, and if you take the length of it and square it, of course that is your little c squared. Well, what is c itself? C is a minus b. Well, what is the square of a length? That's dotting something with itself. So a minus b dotted with a minus b. That's the idea we had last time. How do you dot two expressions? So the idea of FOIL that you had is still applicable. Just step by step you can apply it. A dot b with minus, b dot a with minus, b dot b minuses cancel each other, and I get b dot b. Once again we say a dot a, our convention was to write this thing a squared. B dot b, just like that, that's also little b squared. This is minus, they are the same thing. Remember we said this is symmetric, you can write it a dot b or b dot a, so I can write it that twice a dot b. So little c squared is equal to this expression, but from high school we remember little c is also equal to that expression. So over there we had little c from law of cosine. This was a squared minus 2ab cosine theta plus b squared. Well, this c and that c are the same thing, so these two middle terms have to be the same. So a dot b has to be same as little a times little b times cosine of theta. Another way of writing this, it was the length of a, this was the length of b, and that's a cosine of theta. Most common use, again going back to a user point of view, if you want to calculate the angle, for example, first you calculate the cosine by doing the dot, dividing by the length of individual vectors, and then you apply arc cosine to this. So let me correct this thing. So again, let me repeat my mantra. As an end user, you come and use this thing, that's fine. Many engineering application, you want the angle, you want to move on. But higher level up, where does that formula itself come from? From this type of reasonings. Well, you might ask a higher level up of how does somebody come with this kind of approaches. Well, if you spend a lot of time in mathematics, you do come up with these ideas, just as when you are applying a lot of time in engineering, you come up with ideas that you were not taught directly, but you think about it on the spot. By being immersed in that topic, these ideas do come to you. You might innovate something as opposed to always just reusing something that somebody else did before. So no different in that respect in mathematics. Next idea that we had last time was the idea of a projection. Let me go ahead, add a little side note to that, and then we do the projection itself. So the idea of projection was that you have one vector, let's call it A. Try to avoid U and V because in handwriting they are not easy to tell them apart. So A and B, you can go wrong with that. So the idea of projection was we drop a perpendicular from one of these vectors on the other one, and that here's the projection. Let's call it the vector C. So C is the projection of B on A. So A is playing the role of the screen, B is the object, C is the shadow of the object on the screen. That's a thinking that we have here. Question is, what's the length of C and what's the vector C itself? For the length of C, let me just write down a formula that wasn't in the lecture, but you can easily extract it from the formula we did have over there. How long is C? Well, very simple idea. Take A and B and dot them. That number could be positive or negative. Given that this is always positive, we convert this thing to positive and divide it by the length of A. So this is the length of the projection, not the projection itself. The length of projection as a positive number is always this. Well, what if you didn't want to use the absolute value? Then you have to make two different formulas. Length of projection. In case your angle, so let me write it here. If you have dealing with a situation, this angle theta is an acute angle. So your projection lines up with the A itself. In this case, A dot B, we said last time, is positive, so I don't need to take any absolute value out of it, and divide it by the length of A. So this is the acute case. And in case you were dealing with so this was A, this was B, again A. Now what if this angle theta was between pi over 2 and pi? That's an obtuse case. And if you want to catch the length of C, so what's the issue here? In this case, when you drop the perpendicular and you make your shadow here C, C does not line up with A, it goes in the opposite direction. So what about that? Well, then A dot B will be negative while this is positive. So to compensate for that, you have to multiply it by another negative. So to cover both of these cases, we put the numerator in an absolute value. It's absolute value of a number, not to be confused with the denominator, which was the length of that vector. Same idea anyway. So well, where does this come from? Very simple. This is just very basic trigonometry. Let me just do the first case. So this was B, this is A, and the angle is the acute angle, and the projection of B lines up with A. So again, let me extract this. If it was trigonometry, this was length B, and this was length A, and this was angle theta. You would have said what? You said that cosine of theta is the adjacent to hypotenuse. So adjacent is the hypotenuse times the cosine of the angle. But the adjacent is what now we renaming as the length of the vector C. So C is just x in this formula. B is the length of the vector B, so I can write it as the length of vector B, and then I have cosine of theta. Okay, so this is what you have seen in trigonometry. What does it have to do with the dot product? very simple. I am going to go ahead multiply this by length of A and divide by length of A. Why do I do that? Because I want to bring the dot product in the picture. A dot B dot cosine of theta, excuse me, length of A times length of B times cosine of theta, that is A dot B, and the denominator is just length of A. So length of the projection is A dot B divided by the length of A, in case where this was an acute case. So in case of obtuse, you can do it yourself. You'll see you quickly get the same answer. So our formula is established. Now we actually had the formula for the vector projection, meaning if this is the vector B and this is the vector A, and I want to catch this, the vector C, not just the length of C. The formula we had was a bit more involved. C, what was it? A dot B over A dot A times A. So the screen vector, the vector that acts like our screen, shows up 4 times, twice in numerator, twice in the denominator. The object vector B shows up just once in the numerator. If you wish, you can rewrite it like this. Denominator is the length of A squared. Okay, where does this thing come from? Well, it's very simple. We can let me again assume that we are dealing with an acute case. So this is a vector A, B. Last time we said over here, we said the length of the vector C, the length of the vector C was A dot B over A. Well, what is the vector C itself? Vector C is the length of C times the unit vector in the direction of A. Is that right? If I want to make this vector, all I need to do is to find a unit vector in direction of A and multiply it by the length of the vector I want. So instead of C, I'm going to put its equivalent value. So it was A dot B over A. And unit vector in direction of A. Well, unit vector in direction of A is A divided by the length of A. So by now I have A dot B over the length of A squared times A, that A is this A here. Another way of writing this, we said last time, you can dot a vector with itself. So that establishes that idea of the formula for the projection. For the obtuse case, very similar. Again, I leave that to you to do. Next statement that we made was the so-called Cauchy-Schwarz inequality, that A dot B is less than norm of A times norm of B, and that is more than the negative of the same thing. All that essentially boils down to the fact that cosine of theta is between 1 and -1, so the maximum you can have is the product of the length, and the minimum that you can have is the negative of that. So we essentially proved that already in the lecture last time, so I don't spend extra time on that. So just to remind you, if you come across the name, here is a Swiss mathematician, Cauchy-Schwarz inequality. Then you have something more significant than that, the so-called triangle inequality. Triangle inequality. So we said there that if you add two vectors and then take the length of it, it's less than if you take length of each of them and add them up. That's called triangle inequality, because if I have A and then B, and then I make the sum of these two, which is A plus B, well, it stands to reason that going straight is going to be less than or equal to sum of the two other short trips that we have made. So, well, how do we establish this thing as a theorem? Here's one way. We can say A plus B squared is equal to, well, what is that? A plus B dotted with A plus B. We learned how to dot this thing last time, so I do this thing quickly. So A dot A is same as A squared, B dot B same as B squared, and A dot B and B dot A, they are the same thing, so I write it as 2A dot B. Now 2A dot B is less than length of A times length of B, so I copy A squared plus B squared. This is less than or equal to, because this is, I'm being replacing it by the length of A times the length of B. Well, now you know from your high school algebra, this is simply length of A plus length of B, the whole thing squared. Now if I take square root from both sides of this inequality, I get the triangle inequality that I had up there. So that finalizes case of triangle inequality. The last item I want to mention today is the statement of Pythagorean theorem in 3 dimensions. So we started with Pythagorean theorem. The standard form of it is in 2 dimension, but we also have occasion for using it in higher dimension. Let's go ahead. Suppose we have a 3-dimensional situation. y, z. Now suppose I have a point in space whose coordinates are a, b, and c, and the length of this line is d. What we want to show is that d squared is equal to a squared plus b squared plus c squared. This is similar to what you had in 2 dimension. In 2 dimension, if you have one point with the coordinates a and b, then the length of the line that connects that point to the origin is just square of the length is a squared plus b squared. In higher dimension, it's sum of square of all the dimensions that you got. That's higher Pythagorean in higher dimensions. How do we establish it and see it directly? One good way to go about this thing is to actually see it in statement of about the box. So what I do is that I'm going to complete the box here. I'm going to drop a perpendicular. So hopes that my drawing is reasonable. Well, it is not reasonable, maybe. Let's see. So what we mean here is that if I have a box with dimensions a, b, and c, then the inner diagonal of it has the following relationship between itself and the 3 sides of the box. So inner diagonal square is sum of the square of all the sides. So in 2 dimension it would have been a rectangle as opposed to a box, and your dimensions are a and b, and this one you call it c or d or whatever it is. D squared is equal to a squared plus b squared. In 3 dimension is sum of square of all 3 of them. Why is that true? Okay, again, you want to stop this thing and see if you can cook up reasoning that leads to this formula. Perhaps you want to get a bit of a hint here. There's always a line that helps us actually establish the theorem. So let's see. I draw a line from corner to another corner on the face. Now if you pay attention, this is what kind of a triangle? If you said the right triangle, you are the grand prize winner. So this is a right triangle here, because this side is perpendicular to all the sides on this triangle. Now this is another right triangle. So in 3D they don't look like right, but if you consider the perspective, it is. So if this is A, what is this side? Well, that's going to be same as that. It's going to be B. Therefore this, as a hypotenuse of the triangle, is going to be A squared plus B squared. So this is radical A squared plus B squared. This side is the third side here, C. To find the hypotenuse in this yellow triangle, you have to square this thing and square that one and add them up. So D squared is going to be the square of the bottom side, which is A squared plus B squared, and then the third side here is C squared. So when you simplify it, you get A squared plus B squared plus C squared. So same idea can be applied in a higher dimension, but of course in 4th or 5th dimension we cannot draw any reasonable picture. So when you come across the so-called distance formula in higher dimensions, where does that formula itself come from? Well, that's essentially just a Pythagorean theorem extended to high dimensions. Okay, so in this lecture we collected a lot of little theorems from geometry, trigonometry, that we showed how they apply directly to linear algebra. Essentially the formulas in linear algebra are more advanced, clean-cut version of those, and we are going to try to use the notation that you see in a linear algebra class. Now future lectures, there are going to be fewer proofs of this type. We are going to go back to the applied and user approach, but every now and then we are going to digress and come back and try to explain the reasoning behind some of the ideas we had. So until the next lecture, where we are going to have a new section, good luck and God bless.